Here's another definite integral, and as I've been saying in the previous few videos, if you have a definite integral and you have learned what an improper integral is, what you're going to want to consider every time you look at a definite integral from this point forward is whether or not the integrand, whether or not this function sitting right here, is discontinuous at or between these limits of integration. And in this case, it should be pretty obvious. This integrand, 3 over x squared, that's discontinuous at 0. That function's undefined at 0. And 0 is smack dab in between these limits of integration. And so when you have an integral and you recognize that it's improper because it's discontinuous between your limits of integration, what your first step is going to be is to break that integral up into the sum of two separate integrals. So we can do the integral from -2 to 0, right? This would be the area bounded by this curve in the x-axis, the signed area between this curve and the x-axis on the interval from -2 to 2. Well, we can break that up into that signed area from -2 to 0, and then we can add on the rest of the signed area from 0 up to 2. So we would break the integral up like this. Now, what you have going on within each of these integrals is you have another issue. This integrand, 3 over x squared, is undefined at the upper limit of integration in the first integral. In the second integral, the integrand is undefined at the lower limit of integration. If you hope to use the fundamental theorem of calculus in order to evaluate this integral, what you're going to have to do at this point is you're going to have to get rid of those issues. You can't use the fundamental theorem of calculus unless your integrand is continuous at and between your limits of integration. So in this first integral right here, what we're going to do is just kind of pick a dummy letter. I'm going to go with a, and I'm going to replace that upper limit of integration where my integrand was discontinuous. The integral itself, the integrand itself, is not going to change on this line. What is going to change, though, is the upper limit of integration, and I need to give that a way to approach this number, but not quite ever get to it. So I'm going to let a approach 0. But on this interval from -2 to 0, I would only be approaching 0 from the negative side, from the values slightly beneath 0. Similarly, we're going to have to do something with this integral. We can't have this lower limit of integration being a value where the integrand is discontinuous. So we replace that, and I'm not going to use the same letter. Let me use a different letter. I've already used A. So I'll go with B for the second one. So I'm going to pick some dummy letter to get that lower limit of integration out of there. The integrand is not going to change, but I do need to let this integral have the lower limit of integration, B is the letter I chose to represent it, approach 0, and I want to only approach 0 from the bigger side if I'm an element of this interval. From 0 to 2, my values would be slightly bigger than 0, so I would let B approach 0 from the bigger side. So at this point you have kind of two pieces of work to do. You're going to have to evaluate this integral and then a limit, and then you're going to have to evaluate this integral and a limit, and then you're going to add the two together. Now the nice thing about this process is if you go through this first half of the problem and get an answer of infinity or negative infinity, if you get that this integral here diverges, you don't even have to worry about this one. The sum of the two integrals is then going to diverge. So when I'm in a situation like this, I kind of just handle half of the problem, and that way if that half diverges, I haven't wasted my time by continuing to do the other half of the problem the whole way down my page too. So I'm going to go ahead and at this point try to develop an antiderivative for this expression here. So now I'm going to use the fundamental theorem of calculus. This is 3x to the -2nd, right? That integrand would be 3x to the -2nd if I wanted to write it in equivalent form. I could add 1 to this exponent to turn the exponent into a -1. And then I would just have to divide by that new exponent. Divide by -1 is just going to make that coefficient negative. I'm going to have to evaluate this from -2 up to a and just kind of see what happens. So now I'm going to be checking a limit as a approaches 0 from the smaller side of, I'm going to simplify this I guess before I toss in a and -2 and then take my difference. So I'm going to write this as -3 over x, right? I'm just rewriting it without the negative exponent on it. I still need to evaluate this at a and at -2 and take a difference. So when I do that, I'm looking at a limit as a approaches 0 from the smaller side of negative 3 over a, right? So I'm putting a in place of x, and then minus negative 3 over negative 2. So I know I have a lot of negatives floating around here. We'll try to clean that up on the next line. At this point, I have an a that I want to attempt to put 0 in place of. I want to try to evaluate this integral. So what I'm going to end up with is I'm going to end up with negative 3 over a number slightly smaller than 0. This right here, negative and a negative, will be a positive. So that'll then be minus positive 3/2. The issue that you have right now is with this piece. Negative 3 divided by negative 1/1,000,000th. That's like negative 3 times the reciprocal of negative 1/1,000,000th times negative 1,000,000. That's going to give you negative 3 million. Now, as this 0 gets closer and closer, as this denominator gets closer and closer and closer to 0, you can let it go from 1/1,000,000th to 1/10,000,000th to 1/1,000,000,000th. You're going to have, when you multiply by the reciprocal, a quantity here that's getting larger and larger and larger. This limit is going to be infinity. This integral right here diverges because that limit was infinity, and therefore we don't even have to worry about the second part of the problem. If we wanted to, we could go down through this and we would see that we'd get infinity or negative infinity for that. And our overall integral, our original integral, is going to be an integral that doesn't equal infinity. When an integral doesn't converge to a specific value, we're just going to say that the integral diverges. If we would have gotten a number here, let's say that this would have been just, for whatever reason, if this turned out to be a 1 in this denominator, negative 3 minus 3/2, we got an actual value here. At that point, you'd want to go back and carry out the second half of the problem down this column and see if you got a value for that. If you did, you just want to take the sum of those two separate answers, and that would be the result for your original integral. But if one of your two pieces that you're breaking up into diverges, your overall integral also diverges, and that was definitely the case here.